Okay, so standard normal very random variable, as I said, it's usually indicated by this uppercase Z, and it's CDF. Sorry, this is PDF and this is CDF. They're usually indicated by this phi, lowercase phi and uppercase phi in Greek letters. Phi x indicates the standard normal PDF, and this is the standard normal CDF. And I have stated that any normal random variable x can be standardized by subtracting mu from it and dividing by the standard deviation. So this standard deviation is something constant, so this becomes a linear transformation. So this its expected value, for example, of this is going to be 0 if you take a look at this, and its standard deviation of z is going to be 1. So this standardizing actually is used a lot in standardized scores, for example, in entrance exams, or we also, this is sometimes called, this is a random variable, but for a particular x. Imagine we have a particular specific x from this distribution. And you may wonder how much standard deviation, this is called the z-score of that variable, and it actually shows, let me go back to GIMP. So what I'm trying to say is that we may encounter the standardized normal variables. Here's a real life example. Imagine we have student grades in a course. The total grade at the end of the semester has mean is centered around 60. We have the mean grade of 60, and the standard deviation is 10. All right. Now, if a student gets a score of 80, okay, if a student gets a score of, let's call it S, the row score, if he gets if student gets a score of 80, one thing we may ask is that, for example, how likely is this? So what is the probability, for example, to have a student to get a grade of total grade of 80 or more? Or how important is this score 80? We actually measure it by what is called a standardized score, and the way to get the standardized score, which is also sometimes called the z-score, is this small lowercase z, is how far we use this, which actually tells you how much standard deviations it is away from the mean. Okay, so let me repeat that sentence. 80 in this non-standardized form, the score of 80, how many, I said how much standard, so how many standard deviations, so it's something countable. So how many standard deviations this grade of 80 is away from the mean. In order to do that, how many standard deviations we have until 80 from 60? So from 60 to 70, one standard deviation, another standard deviation to 80, so we have 2. Okay, so it's the z-score of this student is 2. And a student who got, for example, 45, how much standard deviations away from 45 is from the mean? We are going to do the same thing. By the way, yeah, exactly. So we are going to, in this other case, it's going to be 45 minus 60 divided by 10 is going to be minus 1.5. Okay, so as you can see, this is like also sign distance. A student who got a score less than the mean is going to have a negative z-score, and it shows, and this 2 minus 1.5, these will be standardized entities. For example, even if we measure the score in another unit out of 140, okay, if the maximum score you can get is 140, and again we measure the scores, and for example this time it's the average is around 80, the standard deviation is 25. If we have something like this, again, if somebody gets, for example, 105, if this is the score, we can compute its z-score by again subtracting the mean from it, which is 80, and dividing by 25, which is going to be exactly 1. Okay, so this person is 1 standard deviation away. And this 1 standard deviation away, 1.5 away, minus 1.5 away, it will be standardized no matter if the score was 1400 and where the averages is 800 and standard deviations 250, for example. A score of 1050 will still exactly have the same z-score of 1. Okay, so this is sometimes called the standardized score, and these standardized scores are used a lot in comparing maybe exams that have different scales. So this is like sometimes this is called normalization. We normalize things together to have the same unit. Standard normal form has actually it's going to be unitless when you do this. If you divide for example kilograms by kilograms, I mean if this was like kilograms, all right, the weight of some motorcycles, for example, this may be weights of motorcycles, and with average weight this, with standard deviation this. When you standardize, when you do something like this, x minus mu divided by standard deviation, the unit of this z, as you can see, is no longer kilograms. You get away from kilograms to some imaginary standard unit. That's why it's unitless. So this is kilogram, this is kilogram, kilogram divided by kilogram, it has no unit. Okay, so it's some standard normal score, which is between minus infinity and infinity, centered around 0. It's no longer 0 kilograms, it's no longer 1 kilograms. This, most of the time we say that it's, for example, it's that many standard deviations away from the mean is what we refer to this standardized z-score. All right, and the main reason we use this standard normal formula is because the table are given to us in the standard normal form. Certain probabilities you're going to see like the probability of 0.95, 0.9, 0.975. These are like standard confidence values, confidence thresholds that people use. And we will have certain meanings for those, certain percentages. So let's take a look at and try to solve these examples. Like, and also if you look at this, this CDF variable, since it's symmetric, the table is only provided, I mean, we only need one part, the negative version, let me take a look and show you let me try to tell you what it means. So if we have a standard normal form, and if somebody asks that, what is the probability? For example, if this is x here, we have the minus x here. What I'm trying to say is that if you have the CDF value, this is capital Phi, if you know CDF of x is something, if you know the area under the curve on this side, this will be equal to whatever this is. If I ask you what is the CDF of minus x, can you tell me what it is? Can you write in the chat box? If CDF of x is, for example, let me tell it's a, okay? If CDF of x is, again, this is CDF, not PDF. If CDF of x is a, what is the CDF of minus x, which is the area under the curve right here? Exactly, it's equal to 1 minus, it's equal, this area under the curve on this side, since it's symmetric, this area is equal to this area, which is 1 minus a. Both of them are correct. So 1 minus CDF of x, 1 minus a will be this. Yeah, in this, for example, there's a chance to get higher than max score. Oh yeah, exactly. When you're very good, a very good observation. When we assume that everything is normally distributed, it's not bounded. The normal variable is between minus infinity and infinity, right? So if we say that the grades are normally distributed with mean is equal to 80 and standard deviation 20, for example, you're absolutely right. It means that the grades are normal distributed, and it's a non-zero probability to get a grade of 200. Actually, in our case, it's impossible, right? We have a maximum grade. So this is like basically an approximation. The normal distribution in that case will be an approximation, because in our case, if 100 is here, for example, in our case, the sample space will not contain any grades other greater than 100. They will end abruptly. They have to end at 100. But when we say they're normal distributed, we always give non-zero probabilities even to higher values. This is a very good point. When we use normal distribution, there is always a probability to get infinity. So when you use normal distribution to model the weight of fish in a lake that you catch, it's possible catching a fish of 10 tons, 100 tons is still non-zero. Okay, that's a probability. But practically, this is what it's also saying here, right? This sentence. Practically, for values z greater than 3.9, okay, after 3.9 standard deviations, for example, if this is 1 standard deviation, 2 standard deviation, 3 standard deviation, 4 standard deviations, in the standard normal form, after 3.9, it's practically 0. So it will be practically impossible to get a grade of maybe larger than 100, or maybe depending on how your distribution is. So it's the area under the curve after a certain number of standard deviations is going to be infinitesimally small, which can be ignored. So therefore, I say this normal is like an approximation to the real thing, because I mean, mathematically, they go all the way to infinity and minus infinity on both sides. But practically, after 3.9 standard deviations, it's, look at this, it's saying it's approximately equal to 0. Okay, you may think after 3.9 standard deviations, they touch the x-axis practically, and therefore we have this. So CDF of 3.9 is very close to 1. Okay, CDF of 3.9 means that the probability to have a value 3.9 or less in a standard normal variable is almost 1. And the table is not provided below these values. All right, so here are some values. Even look at this, the CDF of 1.35 is 0.91. It's, I mean, 0.91% of the entire area of the curve is 1.35 standard deviations away from the mean. So if this is your standard deviation, if 1.35 is this, for example, if this is 1.35 here, actually it doesn't, it's not consistent with what I had written earlier, but if this was 1.35, it means that the 90% of the area, 91% of the area is to the right-hand side. 9% lies here in only 135. It's a very small z-score, right? Z-score, I mean, or z-value, 135, only 9% of the area is towards the right. And when z becomes 3.9, it means it's almost impossible. The area under the curve to get more than 3.9 is practically 0, very close to 0. So here are some standard values. So this is the same example like that I gave, like the relationship between z and minus z. Okay, 135 and minus 135, and it's the complement. This is the complement, and this is also this is something else. Okay, 0 point is asking 0.77. Are we going to solve this example? Let's see, maybe not. Let's start solving an example from scratch, both of these 411 and 412. We can take a look at this other example, 4.10, later. Okay, so let's take a look at this 411, computing non-standard normal probabilities. So suppose that the average, let's try to solve it without looking at the solution first. Okay, the average household income in some country is 900 coins. So probably this is in medieval times where we still get the income in coins. Okay. Oh, maybe it's bitcoins. Maybe it's some future time. You may consider this as a medieval time, or maybe in future time, in 200 years, we will have our household income in bitcoins. Okay, so imagine it's the average is 900 coins and the standard deviation is 200 coins. Assuming the normal distribution of incomes, compute the proportion of the middle class, whose income is between 600 and 1200 coins. All right, so how much of the population, what percentage of the population get coins between 600 and 1200 coins? So what we need to do is, so mean is, this is our original income, random variable is this, with mean 900, standard deviation of 200. All right, so we are asked what is the probability, what is the proportion of the population which gets income between 600 and 1200. Okay, we are asked this. So in order to do that, we have to standardize everything here. When you standardize this, 600 minus 900 divided by 200. So the probability will be equal to your standardized random variable where it's z, okay, in which, so z is x minus mu, or x minus 900 divided by 200. This is our standardized variable. And the probabilities that we're asked, we need to also standardize. What is their value in the standardized form? We have to do it for them as well. So this is going to be minus 300, so minus 1.5. So minus 1.5 standard deviations below the mean. And this is 1.5 standard deviations above the mean. So all I need to do is, so we are asked something like this. We are asked something symmetric. Okay, if this is 0, we are asked 1.5 and 1.5 here. If you take a look at the CDF of 1.5, this is minus 1.5. So we are asked the area that is here. So which is going to be, if you look at, if the CDF of 1.5 is equal to A, okay, what do I need to do? If this is, I need to subtract from A 1 minus A, right? So it's going to be whatever A is. So the probability that I'm looking for, so the CDF of this part, yeah, it's going to be 2A minus 1, exactly. So so this, if the CDF of 1.5 is A, this area under the curve is going to be 1 minus A. So I need to subtract from A. 1 minus A is going to be subtracted from that. It's going to be 2A minus 1. Exactly right. So all you need to do is look at the CDF of 1.5 and compute this. CDF of 1.5, let's take a look at, we can actually go ahead and take a look at the table. So where's the, yeah, CDF of 1.5 is 0.9332. So 0.9332 is what A is, 0.9332. Multiply it by 2. Let me do it. Where's my phone? 0.9332. 0.9332 multiplied by 2 and subtract 1 from it, minus 1. 86%. This one becomes 0 point, actually close to 87. If you round it to two digits after the decimal point, 87%. So 87% of the population, which is here, the exact number, is actually in the middle class, quite many. Okay, and so this is how we solve this problem. Now, let's take a look at the inverse problem, in which this time we're going to be given a proportion and asked what is the z value, or what is the coin value in the same country. Okay, so look at this example for point 12 at the bottom of your screen. The government of the country, now this time, they decide to issue food stamps to the poorest 3% of the 2a minus 1 part. Okay, let me, before continuing on for 12, let me try to clarify this. So you understood hopefully the standardized part, in which we try to find the probability of that x is between 600 and 1200 with this mean and standard deviation that was given in the question. When we standardize our variable, we subtract the mean and divide by the standard deviation that is given in the question. So which means that when these entities, a coin, 600 coins per year income, it should also be standardized to standard z-score by subtracting mean from it, 900, and dividing by the standard deviation. So this means that it's minus 1.5 standard deviations away from the mean. They receive that many coins. And this one is 1.5. So in this question, we were lucky that when we asked this probability, they were all equal distance from the center. So we were asked, what is the probability? So if you look at this probability that we try to find in standard normal distribution, okay, the probability that the z value is between minus 1.5 and plus 1.5. Let me try to explain it on a larger figure. So this is where 0 is. So this is our standard normal distribution. Okay, this is where 1.5 is, and this is where minus 1.5 is. Now, since this is symmetric, okay, I didn't draw it as symmetric. It doesn't look symmetric at all in my figure, but assume that it is symmetric, which means that if it's symmetric, the area, the tails, I mean, I have to draw it symmetric so that you understand it better. So let me try to maybe put 1.5 here and the other 1.5 here. At least the areas look clear. So imagine this, what I have drawn here is symmetric. What will happen is that the areas under the curve to this side and to this side, they are equal, right? If this area here is A, now I'm calling, maybe let's call this something else. Let's call this area B. This area will also be B, all right? Now, here, in order to compute the probability between minus 1 and 1.5, what do I need to do? I need to subtract the CDF of 1.5 minus CDF of minus 1.5. This is the probability that I'm looking for. The area under the curve that is in between, the solution that I'm looking for, that I'm asked, what is the population ratio of the population that are here on this green curve, which is given by CDF of this, which is the area to the left-hand side here, subtracted with the area on the curve to the left-hand side of minus 1.5. So this is our solution. Now, in order to find this solution, I call this A. What if the CDF of 1.5 is A? So the area, if we call this area entirely to the left-hand side A, what happens is that if you look at the relationship between A and B, okay, A plus B equals 1, right? I mean, if the area under the curve to the left-hand side, I called it A, I call the CDF of 1.5, sorry, CDF of 1.5, I call this A, and then this area B becomes 1 minus A, right? Because this is the entire area under the curve is 1. Therefore, B is equal to 1 minus A. B is equal to 1 minus A, which is also the CDF of minus 1.5. So in order to solve this, what I need to do is A minus B, which is this 1 minus A. So I write 1 minus A like this. If you solve this, it's A's become, this is plus, it becomes another A, so it becomes 2A minus 1. So this is not a formula actually that used in the book. I mean, I just name them variables like this. It's just, all you need to do is find the CDF of this and find the CDF of this minus 1.5. The thing is that the CDF of minus 1.5 is 1 minus the CDF of this thing. Okay, whatever the CDF of this thing is, 1 minus that CDF is this, the negative Z CDF. So that's why we had this. You don't need to memorize anything about 2A minus 1 or anything. Now, let's go to this inverse problem, which is this time we're not asked a probability, but we're asked a coin threshold. So here, if you look at this problem, the government of the country in the same example in 9.11 decides to issue food stamps to the poorest 3% of the households. Below what income will families receive food stamps? So now the question we're asked is this. We have this 900, nice 900 with a standard deviation of 200. Okay, so this is mean. So below certain threshold, so we are interested in the poorest of the families. Now, here we want to give food stamps to 3% of the population, which means that the area under the curve here, so if this curve indicates the histogram of the entire population, the area under the curve to the left-hand side here is we want to figure out what is the amount of coin. So this is this big question mark we are asking this question. In what question mark, in less than that question mark, 3% of the population lies. All right. Now, again, we may standardize this and ask the same 3% is going to occur so we are going to look something like this. We need to look at the CDF of something. What is the z-score of this? Let's try to figure out the z-score. And if you find that z-score, you can also get back to the original variable by multiplying that z-score with that standard deviation and adding mu to that. Okay, so this is how you're going to get back to x. If z is equal to x minus mu divided by standard deviation, then x is equal to z times standard deviation plus mu. Okay, now all we need to do is, what is this z, this particular z? What is this particular z in which the area to the left hand side is going to be 0.03? So we have to look at the table in such a way that in the table we were going to look at probabilities, and we are going to find a location where the probability is 0.03. Okay, and then this z is going to be probably negative something. It has to be negative, right? Okay, can you tell me, for example, what is the, let me ask you, what is 0.5? What is z for 0.5? The area under the curve, 0.5. What is that value z here? It is, yeah, 0, right? Because it's symmetric, it's centered around origin. So for z is equal to 0, half of the population lies to the left, half of the population lies to the right. In Octave Online, you can use the inverse CDF function. Exactly. So instead of looking at the table to figure out where to find, there is the inverse CDF function in Octave Online for the normal, standard normal. Let's take a look at that. Standard normal inverse CDF MATLAB. What is that function? Norm inv. Yeah, it's then this function, norm inv. All I need to do is go to Octave Online, and this is the function that I'm looking for, norm inv 0.03. Wow. Oh, I need to load the statistic package, norm, the none package. Wow. Yeah, actually, yeah, this it says non-package. Yeah, package load statistics. Load stat. Yeah, I always forget. I mean, it should be loaded by default, right? Who uses Octave Online? Students working on statistics like us, right? So yeah, it worked. It's minus 1.880. So this is the z value that we have come up is minus 1.8808. So what is the Bitcoin that I need? If you earn less than that many Bitcoins, you're poor. But these days, if you earn Bitcoins, you are never poor, right? But let's assume in the very future time, the annual income is 900 Bitcoins per year, and which means that Bitcoin is devaluated. The devaluation also occurs in Bitcoins. It may be in that case. So if the z-score in this case for 0. It's 18808. So what we need to do is multiply it with 200. So multiply this with 200, add 900 to that, you get your poor family threshold. Okay, so let's take a look at the book on this. Yeah, it's 1.88. It's going to find, yeah, 1.88. You have to multiply 1.88 with 200 and add 900 to that to get back to this, which is 524 coins. So that's the poorness threshold, which is very close to the middle income family, right? I mean, if you earn 600 coins, you're considered middle income. And 86% of the population were middle income. But if you earn less than 512 coins, you're considered only 3% of the population earn 512 or 24 or less coins in a year. All right, so this is how we solve those inverse problems. You may find more exercises at the end of the chapter. And the last thing we have left actually is the central limit theorem. I will just make an introduction to central limit theorem. We are going to continue the central limit theorem on Tuesday. I mean, we are not too behind the schedule, by the way. If you take a look at where we are currently we are ending week 5. And the only thing that is left is central limit theorem, which we will be able to finish in 1 hour. So it's like we're 1 hour behind the schedule. And next week, we're going to start talking about, we're going to jump 4 chapters ahead and jump to chapter 8 of the book, which is how the statistics, population sample parameters and statistics. So central limit theorem is a really nice theorem that says that if you have random variables, x1 to xn, they're independent, but they're distributed with the same distribution. And this is really important. This is the key part. Any distribution. They don't necessarily be normally distributed. They can be from any distribution with some given mu and standard deviation, or with some given variance. So every distribution, whatever distribution it is, we know, I mean, it has to have some variance and expected value, right? So the expected value and variance is an important parameters of any distribution, and they can come from any unknown distributions. So in other words, we have n random variables from the same distribution. This is the central limit theorem. As n goes to infinity, and it doesn't need to be infinite at all. For practical reasons, when n is 30, 40, we still observe approaching normal, okay? So the theorem states that the summation of your random variables as n goes, when the summation is of large number of these random variables coming from any distribution, the standardized form of that summation is normally distributed. It's standard normal. So what it means is that the expected value of the sum, if you sum n numbers with each of them with expected values of mu, okay? The expected value of the sum, because of the linearity of expectation, the expected value of the sum is going to be n times mu, right? You're summing n numbers, each with expected value mu. So this is the expected value. If you subtract whatever your summation is, they are all random values, okay? Random variables. You subtract from that sum the expected sum, and you standardize it by sigma times square root of n. What is sigma times square root of n? By the way, if the individual variances of these variables are sigma square, let me write it here. If this is sigma square, the variance of this s, you define this s as x1 plus x2 plus all the way to xn. These are again independent, and it's a linear combination of these random variables. The variance of s is going to be n times sigma square. If these are individually sigma square variances, the variance of this summation is going to be n times sigma square. If the variance of s is this, what is the standard deviation of s? It's going to be the square root of this thing, which is sigma square root of n, or square root of n sigma. They are the same thing. This is exactly what it is. So if you divide it by the standard deviation of the sum and subtract from it the expected value of the sum, in other words, if you standardize the sum, no matter what the underlying distributions of these individual variables are, what you get at the end is always standard normal. It's a very strong theorem, right? That's why it's called the central limit theorem. So it works for values of, as I said, n, 30, 40, 50, and we will be using this, for example, when we make inferences, when you're predicting probabilities of something. We will conduct simulations and we will be predicting probabilities. And this central limit theorem will help us in that regard, saying that how many samples, how many simulations do you need to do so that the final predicted probability is within this much of the actual probability with this confidence. So we will be asking these questions, and it will again be following from the central limit theorem. And this is really as strong, as you can see. Any sum, when you standardize it, it is standard normal. All right, and you can, which means that binomial is a summation of Bernoulli variables. It means that it will be normally distributed with expected value mu and sigma, which is mu is equal to n times p. Sigma is going to be equal to this time square root of n, p times 1 minus, or p times q. So whatever the standard, so this one is not the standard normal, so you have to standardize the sum in order to apply this, but which means that this also is applicable for the non-standard case where you compute the mu and standard deviation accordingly for these input parameters. Binomial, gamma, when n is large and when alpha is large here, they will have a shape, their distributions will be very similar to normal distribution for these distributions, okay? It means that you can directly use the standard normal CDF to solve problems related to these summations. So I'm going to continue. I have a couple of slides left here, but we're going to continue on the central limit theorem and the application of it. And also we are going to see normal approximation to binomial problems. We have to be careful about again, continuous versus discrete in this case. When we are asked point probabilities about binomial, how can you, if in binomial case, for example, we will ask, what is the probability of obtaining exactly 5 successes in 10 tries? Okay, if you try to use normal approximation for that, x is equal to 5, that probability is going to be 0 in the continuous case, right? Because normal distribution is continuous, point probabilities are 0 in normal distribution. So we are going to, in order to solve these discrete problems, we will have to extend whatever probability we are asking. We're going to extend it 0.5 units left and right to compute an integral around the probability of that we're asked. We're going to talk about that on Tuesday, and I'm going to stop now. I'll be happy to answer any questions if you have any. All right, so we are going to solve 2 examples and talk about another example on how we approximate binomial problems with normal distribution. All right, let me stop the recording.